in stereochemistry, it's not just important to predict chirality of molecules, but also to be able to draw possible stereoisomers if a compound has stereocenters. And of course, the number of stereoisomers, as we learned before, depends on the number of stereocenters present in a molecule. And the little formula that we used before in order to predict the number of stereoisomers was 2 to the power of n, 2 to n if you like, where n is the number of chiral centers or stereocenters present in a given molecule. Before, we took 2-bromo 3-chlorobutane as an example. So that this is 2-bromo 3-chlorobutane, and clearly 2-bromo 3-chlorobutane has 2 chiral centers, it has 2 stereocenters, and therefore 2 to 2, this gives us 4 stereoisomers possible. So these are, of course, the stereo centers. There are 2 stereocenters, so therefore 2 to 2, so 2 to 2, that is 4 stereoisomers possible in this molecule. Now, we now know that we can use tetrahedral drawings in order to represent molecules. We can also use Fischer projections also. So this time we will draw the possible stereoisomers using Fischer projections. So let's begin with the first one. And of course, as we learned before, we begin with any stereoisomer, and then we draw the mirror image. And to get the third one, we only revert, if you like, one stereo center, or the configuration at one stereo center. And then to get the fourth one, we simply draw its mirror image, so the mirror image of 3. So let's begin with the first one. This is the first one. And of course, using this time Fischer projections. So this is, of course, this indicates the C2 stereo center. This is C3. Okay, so this is one possible stereoisomer. To get the second stereoisomer, we simply draw its mirror image. So to get the second one, we only draw the mirror image, which is this one here. So obviously, the mirror image, of course, remember this is a mirror plane. So as if you put this in front of a mirror, if you like. Okay, so this is the second stereo isomer. So these are two of them, 2 possible stereo isomers now. To get the third one, we keep one of these stereo centers fixed, if you like, or we keep the absolute configuration fixed, but then we reverse the other one. So we can keep this fixed, reverse that one, or keep that fixed and reverse the other one. It doesn't really matter. Whatever you do, of course, in the end, or to get the fourth one, we will draw its mirror image, so it doesn't really matter. Okay, so the third one then would be this one. So if we keep this, or the absolute configuration of this stereo center fixed, okay, and then we reverse the other, we change the other, so we get hydrogen here, therefore, and Cl. So it was simply these 2 groups swap positions. So this is the third stereoisomer. To get the fourth stereoisomer, then we draw the mirror image of 3, and it is this one here, simply just the mirror image, again as if you put 3 in front of a mirror, if you like. Okay, so this is stereo isomer 4. So these are the 4 possible stereoisomers, okay, using Fischer projections this time. Now, if you look at the stereoisomers number 1 and 3, and since there is a mirror plane, okay, or since there are mirror images, and of course it will not be possible to superimpose them on each other. So therefore, they are non-superimposable mirror images. So therefore, the stereochemical relationship between 1 and 2 is enantiomer. So the 1 and 2 are actually enantiomers. So 1 and 2. The same stereochemical relationship applies to that between 3 and 4. 3 and 4 are also a pair of enantiomers. They are mirror images, but they are non-superimposable on each other. So therefore, 3 and 4 are also a pair of enantiomers. So these are enantiomers 1 and 2. And 3 and 4. And as you might predict, the stereochemical relationship between 1 and 3 and 1 and 4, and that between 2 and 3 and 2 and 4, is that they are diastereomers because they are non-mirror images. Of course, if you look at 1 and 3, clearly they are not mirror images. Clearly, obviously, they are not enantiomers because they are not mirror images to start with. The same thing applies to that to the relationship between 1 and 4, 2 and 3, and 2 and 4. So the stereochemical relationship between 1 and 3 and 1, 4 are diastereomers. The same description should be given to that to the stereochemical relationship between 2 and 3 and 2 and 4. So 1 and 3, 1 and 4, 1 and 3, 1 and 4, 2 and 3, and 2 and 4 are diastereomers. So these are diastereomers. They are not mirror images, if you recall. So again, stereoisomers, therefore, can either be enantiomers or diastereomers. Of course, they are enantiomers if they are non-superimposable mirror images. If they are not mirror images to start with, then the stereochemical relationship between them are diastereomers. So this is, again, to conclude now, this is an example of a molecule with 2 stereocenters, and based on that, 4 stereoisomers are possible, and we can use not only tetrahedral drawings in order to represent molecules, but also this time we could use Fischer projections. And again, 2 pairs of the stereoisomers are enantiomers. Any relationship between any other 2 are diastereomers.